In the following examples, I'm going to go through a bunch of explanations of different derivative rules from this chapter. Specifically in this chapter, we've been looking at exponential rules, including natural logs, including e to the x, basically constant values to a power, that type of thing. So started off with a few of those. First of all, I have the derivative of e raised to the cosine of 4x power. What you want to keep in mind here is when you take a derivative of e to a power, it's equal to the same thing. Derivative of e to the x is equal to e to the x. So derivative of e to the cosine of 4x is going to be equal to e to the cosine of 4x, except the chain rule always applies. I always have to take that into account. So I always have to make sure that I take the derivative of the inside function and multiply by that at the end. Okay, so I multiply by the derivative of the inside function. Derivative of cosine, of course, is negative sine of the same thing. And then notice that I have another inside function. Inside function is 4x. So I have to multiply by the derivative of that inside function as well, and we end up with that. Now, you probably want to write this a little bit more organized manner. Probably something like negative 4 sine of 4x times e to the cosine of 4x. But that's your derivative. All right, example number 2, I have the derivative of the natural log of 3x squared. The derivative of natural log of x is just the reciprocal. It's 1 over x. Same kind of thing here. It's going to be the reciprocal, 1 over 3x squared, but that pesky chain rule comes back into play. And so I do have to make sure I take the derivative of the inside function and multiply by that value. So multiply by the derivative of the inside function. In this case, that's 6x. There's a little bit of canceling that's going to happen. I can divide an x out of the numerator. I can take an x out of the denominator. I can divide 3 out of the numerator and denominator, and that's going to end up leaving me with 2 over x. By the way, these natural log derivatives can be done different ways. For example, I could come back and I could also use different log properties. For example, this is the natural log of 3 times x squared. I can break a natural log product up into the natural log of 3 plus the natural log of x squared. And I can even go farther than that. I can swing this exponent around out in front and make that 2 times the natural log of x. Well, you say, well, why is that good? Natural log of 3. Natural log of 3 is a constant. The derivative is going to become 0 there. That's just gone when I take the derivative. Meanwhile, I have a constant times a value over here. Well, I know the derivative of that's just 1 over x multiplied by 2, and that also gives me the same 2 over x. So several different ways that you can do those natural log derivatives. Okay, next example. Looks horrible. It's not. Okay? E and natural log are inverse functions, or specifically e to the x and natural log of x are inverse functions. So if I take e to a natural log power, those two things basically counteract each other. If I take a natural log of e to a power, they counteract each other. What's going to happen in this case? That's actually just going to be equal to sine of 3x. Now, be careful here. That's just an algebraic simplification. There was no calculus there. There was no derivative. I still need to take the derivative here. Of course, derivative of the outside function is cosine of the same thing, and then I need to make sure that I multiply by the derivative of the inside function. Inside function is 3x, derivative is 3. We're going to get an answer here of 3 cosine 3x. Okay? Chain rule, chain rule, chain rule. Can't stress it enough. You're going to see it all over the place in these problems. All right? Next example, same kind of thing. Natural log of e raised to a power. The natural log and the e to the power are inverses. They cancel each other out. It algebraically simplifies to x squared, but I haven't taken my derivative yet. Okay? Derivative of x squared following the power rule, of course, is just equal to 2x. There's my derivative. Okay? I do have one more example that didn't fit on the board here, so let me add that in. The last one I had is the derivative of 2 raised to the sine x power. So I had not done an exponential function with a constant base other than e. Exponential functions are their own derivatives multiplied by the natural log of the base. So that's going to be equal to 2 raised to the sine of x power times the natural log of 2, the base. But remember, you always have to multiply by the derivative of the inside function. Derivative of the inside function, it was simple in this case, it's just cosine of x. And that's my final answer. Again, it's a product, commutative property applies, you can write it in various orders. Basically try to write it in a way that's relatively readable, and you get a solution like that. Just as a reminder, this also applies to e. For example, if I have e raised to the 3x power, that is a constant raised to a power. So it actually follows the same pattern. It's just that I have e raised to the 3x power times the natural log of the base, which is e, and then times the derivative of the inside function. Notice though, natural log of e, I'm basically saying natural log is log base e. I'm basically saying, remember logarithms are exponents, the result is an exponent. What I'm really saying here is e taken to what power equals e? Well, the answer of course is 1. That's why we don't normally put that in there for that e derivative. So again, for your e derivatives, really you can just set it equal to itself times the derivative of the inside function. You don't really need to put that natural log step in there. But I wanted to make the point, it's the same thing that you're doing here with these other values. It's not like the rules change because it's e. It just happens to be that because it's a natural log, that value cancels. So technically you can consider those all to be the same rule, but that's why it simplifies a little bit differently.